Every time heat flows, pressure equalizes, or a gas diffuses through space, billions of molecules are colliding, transferring momentum and energy according to precise physical laws. These invisible processes are not random, they are predictable, measurable, and form the backbone of modern physics and engineering. Transport phenomena in the kinetic theory of gases explain how bulk properties such as viscosity, thermal conductivity, and diffusion arise from the microscopic motion of gas molecules. This framework bridges the gap between molecular-level dynamics and large-scale observable behavior, making it essential for physics, chemical engineering, aerospace science, and atmospheric studies. At its core, the kinetic theory of gases models a gas as a large number of identical molecules in constant, random motion. These molecules are assumed to be point masses with negligible volume compared to the container, interacting primarily through elastic collisions. While this sounds simple, the collective effect of these motions produces complex and highly structured transport behavior. One of the most important transport phenomena is viscosity, which represents a gas resistance to shear flow. In kinetic theory, viscosity arises from the transfer of momentum between adjacent layers of gas moving at different velocities. Faster molecules from a high-velocity layer migrate into a slower layer, transferring momentum through collisions. Remarkably, gas viscosity increases with temperature, contrary to liquids. As temperature rises, molecular speeds increase, enhancing momentum transfer and thus increasing viscosity. This insight is crucial in aerodynamics, where airflow behavior around aircraft depends strongly on viscous effects. Another fundamental process is thermal conductivity, the ability of a gas to conduct heat. From a kinetic perspective, heat conduction occurs because faster, higher energy molecules move from hotter regions to cooler ones, transferring kinetic energy through collisions. The kinetic theory provides an explicit relationship between thermal conductivity, molecular speed, and mean free path, the average distance a molecule travels between collisions. Like viscosity, thermal conductivity in gases generally increases with temperature, a prediction strongly confirmed by experiments. The third major transport phenomenon is mass diffusion. Diffusion describes how gas molecules spread from regions of high concentration to low concentration. In kinetic theory, diffusion is driven by random molecular motion combined with concentration gradients. Molecules naturally migrate to achieve uniform distribution, and the diffusion coefficient depends on temperature, pressure, and molecular mass. Lighter molecules diffuse faster than heavier ones, which explains phenomena such as the rapid spread of hydrogen compared to carbon dioxide. A key concept underlying all transport phenomena is the mean free path. This parameter determines how far a molecule travels before colliding with another molecule. At low pressures, the mean free path becomes large, and classical fluid equations begin to break down. This regime is especially important in vacuum systems, microelectromechanical devices (MEMS), and high-altitude atmospheric physics, where kinetic theory provides more accurate predictions than continuum models. The mathematical backbone of transport phenomena in kinetic theory is the Boltzmann equation. This equation describes the time evolution of the molecular velocity distribution function. By applying approximations such as the Chapman-Enskog expansion, scientists derive macroscopic transport coefficients directly from molecular properties. This is not just theory, it enables engineers to calculate viscosity, thermal conductivity, and diffusion coefficients from first principles rather than relying solely on experimental data. Transport phenomena also play a critical role in real-world applications. In aerospace engineering, understanding rarefied gas dynamics is essential for spacecraft re-entry and satellite design. In environmental science, gas diffusion governs pollutant dispersion in the atmosphere. In industrial processes, heat and mass transfer in gases determine the efficiency of reactors, turbines, and heat exchangers. From a broader perspective, transport phenomena in the kinetic theory of gases demonstrate a powerful idea in physics. Simple microscopic rules can generate complex macroscopic behavior. The random motion of molecules, governed by classical mechanics and probability, gives rise to predictable laws that shape technology and nature alike. If you want to understand how invisible molecular motion controls heat flow, fluid resistance, and diffusion in everything from jet engines to Earth's atmosphere. Subscribe for more deep dive physics content and explore how fundamental theory drives real-world innovation.